Welcome. In this video we're going to look at a couple simple models of the atom, namely the Bohr model and the Lewis symbols. We use that to explain the arrangement of electrons within the atoms and then explain the trend in the sizes of the atoms in the periodic table and the trends in ionization energy of atoms in the periodic table. And we'll be able to predict the typical charges that the A group elements form using this simple model. Then we'll move a little deeper and look at a more sophisticated model involving a quantized model of electron arrangement. We'll identify and name the number of atomic orbitals, show you their shapes and the capacity of electrons within the orbitals. And from that we can then successfully predict the electron configuration of any element on the periodic table. We'll start here with the atom. Around about 1900 it was determined that the atom is not the smallest indivisible particle, but rather it contains subatomic particles, namely electrons and protons and neutrons. The protons and neutrons are almost identical in size, and they reside in the center of the atom called the nucleus. The electrons are almost 2,000 times smaller in mass than a proton or a neutron, and they reside outside the center of the atom, and they are purportedly moving at about 220,000 kilometers per second. I don't know who calculated that, but that's what I read in random fashions. Now the protons have a positive charge of +1, and despite their minute size, the electrons have an equal in magnitude charge, but it's -1. So the protons and electrons are equal in magnitude in their charge, but opposite in sign. A very important and fundamental fact about the atoms is that atoms are neutral because the number of protons is equal to the number of electrons. So we're saying that the total positive charge of all the protons is equal to the total negative charge of all the electrons, which means the net charge of any atom is 0 because the total number of positive and negative charges are equal. A second important fact about elementary particles is that because they're charged, they have properties of attraction and repulsion. You must know that opposite charges attract. Positively charged protons attract electrons, whereas like charges repel. So negative charged electrons repel other negatively charged electrons, and likewise protons repel other protons. Now scientists have identified 118 different elements, different kinds of atoms in the universe. And they're listed on the periodic table, which you see here. And they're numbered, beginning with number 1, which is hydrogen. And moving to the far right, we have helium. And these numbers, 1 and 2 and so on, represent the number of protons in the atom. So each element has a unique number of protons. Or put another way, each element with a different number of protons is a unique element. Now they're listed from left to right and then top to bottom in rows. So the third largest element is lithium, then beryllium, then slide all the way over to here, boron, carbon, nitrogen, oxygen, fluorine, and neon. Neon has 10 protons. The 11th element, 11 protons, is sodium, then magnesium, and then over here to aluminum, silicon, phosphorus, sulfur, chlorine, and argon. That's the first 18 elements. Argon has 18 protons. In the fourth row of the periodic table we have elements number 19, potassium and calcium. Then we have 10 of the what are called transition metals. These are identified as being B group elements as opposed to the A group elements. So the A group elements start here, group 1A and 2A, and jump over to here, 3A, 4A, 5A, 6A, 7A, and 8A elements. So again, in the fourth row of the table we have potassium, and calcium. Then we have 10 of these transition metals from scandium to zinc. And then we come back to the A group elements, gallium through krypton. And so it goes all the way down the table. We'll look in more detail at the order later. When we get down to the 6th period, we find we have element 55 and 56 and 57, and then suddenly there's 72. Well, what happened to the ones in between? They're placed down below here, and these are called the lanthanides because they follow lanthanum. There's 14 of them, and then after we complete those 14, we come back up to hafnium and finish the 6th row. The same discrepancy, if you will, occurs in the 7th period. We have francium and radium, followed by actinium, and then the next 14 are down here, thorium through lawrencium, then back up here to rutherfordium, and all the way across to oganesson. You might wonder why they're taken out of the table, and it's simply because if they were placed in the table would be too wide to fit on the average page. So on the periodic table, we have what are called the A group elements. Groups 1A and 2A, and then 3A through 8A, A group elements, and they are also called the representative elements. For the B group elements, there are 10 columns of them here. Now, in order to understand and explain and predict the reactivity and behavior of the atoms, we need to know where the electrons are situated. So recall that the number of protons is given by this atomic number. Say, for example, magnesium has 12 protons. Well, it also has 12 electrons. We need to know where those electrons are situated, and that's true for all of the elements on the table. We're going to use a very simple model, which isn't accurate, but it's a very good start, and it helps us a lot. Let's take a look at this. So we're going to picture an atom as a circular onion. I would say we cut the onion in half so we can see what it looks like inside. In the center of the onion, we have what we would think to be the nucleus of the atom, containing all the protons and neutrons. The electrons are then situated in various layers. We call them shells in an atom. So in fact, we have 7 shells. Here's the first shell, there's the second, the third, the fourth, the fifth, the sixth, and the seventh. The shells that are closest to the nucleus are smaller and therefore can only hold a few electrons. As we move farther out from the nucleus, the shells are larger and can hold a larger number of electrons. These 7 shells correspond to the 7 horizontal rows, or 7 periods or energy levels on the periodic table. So here's the first shell, the second shell, the third shell, and so on. Now recall that electrons are attracted to the nucleus, and so electrons will fill the shells that are closest to the nucleus first. Much like if you go to a concert, people will fill the front row of seats first. When the front row is filled, then people will fill the second row, and then the third, and so on, farther and farther away from the stage. Likewise, in the nucleus, electrons fill the shells that are closest to the nucleus first. And here and again are these 7 shells or rows in which electrons are placed. So the Bohr model is a very simple model, but it works quite well in giving us a good number of correct predictions. So let's use it first and we'll refine it later. So in this model we show 8 vertical columns. These are the representative or A group elements. And we'll start right here with hydrogen. Hydrogen has 1 proton, that's its atomic number, and of course it has 1 electron because every atom has an equal number of electrons as protons. So whatever protons or neutrons are present, they're in this center gray dot, and then these dotted circles represent the shells, the layers of the onion. And in the first shell we see hydrogen puts its one and only electron. That is, that electron will get as close as it can to the nucleus, and that's in the first shell. Helium is element number 2 off to the right. It has 2 protons and 2 electrons, and those 2 electrons will both be in the first shell. Now I've paired them up to indicate that there's only room for 2 electrons in the first shell, and the shell is full. So I'm pairing them up. Element number 3 is lithium, which is here in the second period on the far left. It has 3 protons in the nucleus, and therefore it has 3 electrons. The first 2 are filling the first shell like helium, and then the third electron is now in the second shell. Beryllium, element number 4 with 4 protons and 4 electrons, has a full first shell like helium and 2 electrons in the second shell. Now, beginning within the second shell and beyond, there's room for more than 2 electrons. In fact, there's place for 4 sites where electrons can go. So what we do is divide that second shell and every shell above it into 4 locations. You could say north, south, east, and west. And each of those locations can hold a maximum of 2 electrons. So let's go back and I'll develop this further as we speak. So here's beryllium, 2 electrons in the first shell, and then its last 2 electrons in the second shell, and we simply spread them out into one of the 4 locations each. It doesn't matter where you put them as long as there's 1 in each of the locations. Boron has 5 protons and 5 electrons. 2 electrons fill the first shell like helium. The next 3 go into the second shell, spreading apart. Now why do they spread apart? Remember that electrons all have the same charge, they're negative, and they repel each other. So they're going to go into one of those 4 locations to get away from each other. Much like when you get on a bus. If you don't know anyone on the bus, you'll find people all sit in separate seats, not pairing up until all of the seats are half filled, and only then do the seats get filled and people pair up. Well, it's the same with the electrons. Here's carbon, element 6, 2 electrons filling the first shell, 4 electrons in the second shell, 1 in each of the 4 possible locations. These are called subshells, if you will. We'll give more clarity to these later, but right now we'll just call them subshells. There are 4 in the second shell. In the case of nitrogen, with 7 electrons, 2 in the first shell, 5 in the second shell. And since all 4 are singly filled, then that last electron has to begin pairing up. There's only 4 locations, or 4 subshells, in the second shell. Here's oxygen with 8 protons, 2 in the first shell like helium, and now it has 6 electrons in the second shell, 2 pairs and 2 singles. Fluorine is element number 9. 2 electrons in the first shell and 7 in the second shell. It's almost full. Neon has 10 protons and 10 electrons. 2 of them fill the first shell like helium, and then the next 8 electrons fill the second shell, and that's as many electrons as can fit in the second shell, a grand total of 8 electrons. Now it turns out that we observe that elements, A group elements with full outer shells, are inert and unreactive. Helium, neon, and argon in group 8A, all the way down group A, those are noble gases. They don't react with anything. They're quite stable and inert. Let's go over to element number 11, which is sodium. Sodium has 11 electrons in total. The first 2 will get as close as they can to the nucleus and fill the first shell. The next 8 will fill the second shell, like neon. And then that 11th electron, there's no room for it in the second shell. It now has to move into the third shell. Magnesium is element number 12. So it's got 2 electrons in the first shell, 8 in the second, and then 2 electrons in the third shell. You may notice that elements that are in the same column have the same number of electrons in their outermost shell. So beryllium and magnesium are both in group 2A, and that's because they have 2 electrons in the valence shell. In other words, that's why it's called group 2A. In the case of aluminum, with 13 protons, 13 electrons, 2 in the first shell, 8 in the second, and then 3 in the third, just like boron above it, with 3 electrons in the outer shell, and that's in group 3a. The outer shell is called the valence shell, and electrons in the valence shell are called valence electrons. So aluminum has 3 valence electrons. Silicon, element number 14, has 14 protons, 14 electrons. 2 in the first shell like helium, 8 in the second shell like neon, and then 4 in the third shell. Here's phosphorus. Phosphorus is element number 15, 15 protons, 2 in the first shell, 8 in the second, that's a total of 10, 5 more go into the third shell. This is just like nitrogen in that respect. It's got 5 valence electrons, and both nitrogen and phosphorus are in group 5a. If we go next to sulfur, element number 16, it has a total of 16 electrons, 2 in the first shell like helium, 8 in the second shell like neon, and then 6 in the valence shell. It has 6 valence electrons, 2 pairs and 2 singles. Chlorine, with 17 valence electrons, has 2 in the first shell like helium, 8 in the second shell like neon, and then 7 in the third shell. In that regard, it's just like fluorine above it, with 7 electrons in the valence shell, and these are both in group 7a. And finally, we get to argon with 18 electrons. The first 2 fill the first shell like helium. The next 8 fill the second shell like neon, and the next 8 go into the third shell. Argon, like the ones above it in group 8a, is inert. It is one of the noble gases. So it turns out that when atoms have a full valence shell, they are stable and inert. We have 2 more atoms we can look at using this Bohr model. We can talk about potassium and calcium. So potassium has 19 electrons, 2 and 8, and 8. That gives us 18 like argon, but the 19th electron has to fit into the 4th shell. And finally, we'll look at calcium with 20 protons and 20 electrons, 2 in the first shell like helium, 8 in the second shell like neon, 8 in the third shell like argon, and then 2 in the 4th shell. Now the Bohr diagram has been simplified in what is called a simplified Bohr diagram. So here, instead of drawing full circles for shells, we draw half circles. Instead of drawing dots for electrons, we simply count up the number of electrons. And instead of drawing a nucleus as a gray dot in the center, we'll write the symbol of the element. So this first symbol is a simplified Bohr diagram of hydrogen with 1 electron in the first shell. Over here to the far right is helium with 2 electrons filling up the first shell. Back over here to lithium with 3 electrons, a full first shell with 2 electrons, and then its 3rd electron in the second shell. So as we move across the second period, or second shell, or second energy level, we're sequentially putting 1 more proton and 1 more electron into each of these atoms, as beryllium is now boron, then carbon and nitrogen, and then oxygen and fluorine, and finally neon. So neon has 2 electrons in the first shell, and that's full, and then 8 electrons in the second shell, and that's full, and it's inert. It's in group 8a with 8 electrons in the valence shell. Here again we have sodium in the 3rd shell, moving all the way across to the right to argon. 2 electrons in the first shell, it's full, 8 electrons in the second shell, it's full, and then 8 in the third, and now argon is inert and stable. And here we have potassium and calcium, the simplified Bohr diagrams. Now, round about 1910 or shortly after there, a gentleman named Gilbert Newton Lewis said, hey, since the A group elements react using only their valence electrons, electrons in the outer shell, why bother writing all the inner electrons? Let's just show the outer electrons. And these are called Lewis symbols. So we write the symbol of the element, lithium, hydrogen, sodium, potassium, etc., and we draw one dot for each valence electron in the atom. And of course you notice that all of the elements in group 1A have one valence electron. And that's why they're placed in group 1A. They are alike in that fashion. All of the elements in group 2A, beryllium, magnesium, calcium, strontium, barium, and radium, all have 2 valence electrons. All of the elements in group 3A, boron, aluminum, gallium, indium, and thallium, all have 3 valence electrons. The elements in group 4A, carbon, silicon, germanium, tin, and lead, all have 4 electrons in their valence shell. Group 5A elements, nitrogen, phosphorus, arsenic, antimony, and bismuth, all have 5 valence electrons. The group 6A elements, oxygen, sulfur, selenium, tellurium, and polonium, all have 6 valence electrons. And the group 7A elements, the halogens, all have 7 valence electrons: fluorine, chlorine, bromine, iodine, and astatine. And then in group 8A, beginning with neon down, all of these elements, neon, argon, krypton, xenon, radon, all have 8 electrons in the valence shell, and they're in group 8A. And along with that we have helium. It only has 2 electrons in the valence shell, but that is full in the case of helium. The Lewis symbols are extremely useful, as we'll see. Using these very simple models, we can actually rationalize some of the trends that we see in the periodic table. For example, look at the relative size of the atoms of these A group elements. As you go down any vertical column, any family, it's pretty obvious that the elements are getting larger down each group. Now why would that be? Well, that's pretty intuitive, because as we're adding more layers of electrons, those electrons are farther from the nucleus. So hydrogen has 1 electron in the first shell. Lithium has 1 electron out in the second shell. Sodium has its outer electron in the third shell, and potassium has its outermost electron in the fourth shell. So it's pretty obvious that they get larger. What's kind of not so intuitive is the fact that the elements get smaller as you go from left to right across any horizontal row. Why would they be getting smaller? Here we're adding, in each case if we go left to right, we're adding more protons and more electrons. Wouldn't you think they get bigger? Well, here again is the same information. This time the data is actually plotted, and you can see it quite clearly. Moving across the first row, helium is smaller than hydrogen. And then lithium is much larger than helium. That outermost electron is now in the second shell. And then going across the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they shrink and shrink and shrink. And then finally, at neon, that's as small as it gets. The next electron goes out in the third shell, and sodium takes a big jump in size. Then moving across the third period, it shrinks again. So this is exactly what we saw in the images here on the left, except now we're plotting it on a graph. And it's true across all 7 periods of the table. So why would that be? Well, let's look at our simplified Bohr diagrams, and I think we can rationalize this. For example, look at the second period. Lithium has 3 protons in the nucleus, attracting the outermost electron. Now it's partly shielded by these 2 electrons in the first shell that are moving very quickly around, so it's shielded somewhat. But there still is a net attractive force. 3 protons blocked by 2 electrons still has the equivalent of 1 proton attracting the outermost electron. In the case of beryllium, now it has not 3 but 4 protons attracting the outermost electrons. In the case of boron, it has 5 protons in the nucleus attracting the outermost electrons. And so we go 6 protons in the case of carbon, pulling the outermost electrons in, 7 protons in the case of nitrogen, pulling the outermost electrons in, 8 in the case of oxygen, 9 in the case of fluorine, and 10 protons in the case of neon, pulling the outermost electrons in. It's got to shrink. Now you might be thinking, but sir, there's more electrons. Doesn't that change it? Well, no, it really doesn't. Think about this as an analogy. Say represent the Earth as being the nucleus, and it's got a gravitational attraction to a stone. So you throw a stone in the air, the stone will fall at a rate of 9.8 meters per second squared because the force of gravity is 9.8 newtons per kilogram. Now it makes no difference if you throw one stone or two stone or 100 stones in the air. All 100 stones will fall at the same rate of acceleration, and they'll all be attracted by the same force, 9.8 newtons per kilogram. Having more stones does not decrease the attractive gravitational force, nor does having more electrons in the outer shell decrease the electrostatic attraction of the protons in the outermost neutrons. So if that makes sense to you, more protons in the nucleus means more attractive force on the outer electrons, then it's very reasonable that, in fact, the size of the atoms moving left to right across any period must shrink. What a simple model explains so well the size of the atoms. Another trend that we can explain is ionization energy. So first of all, what is ionization and what's ionization energy? Here's a model of a lithium atom. A lithium atom has 3 protons in the nucleus, 3 positive charges, and 3 electrons. Its total charge must be 0, plus 3 for the protons and minus 3 for the electrons, for a net total charge of 0. It takes energy to remove or pull an electron away from an atom. It's true for all the atoms because the protons are attracting the electrons. So it takes energy. The energy required to lose the outermost electron is called the ionization energy. Now see if this makes sense to you. If lithium is neutral because it has equal number of positive and negative charges, if you took one of those negative charges away, then it has one less negative charge. It now has to be positive. So here we have again 3 protons, 3 positive charges, but now only 2 negative charges, so the net charge is plus 1. When an atom is ionized, it gets a plus 1 charge. I'm saying it takes energy to do so. And here's the trend in ionization energy for the elements. Notice that the ionization energy increases going up every vertical column, every family in the periodic table. It's increasing as we go up. Now why would that be? Why would it be increasing? Why is it harder to remove an electron? Well, because they're closer to the nucleus in the first period than in the second, right? The outermost electron in lithium is in the second shell, whereas it's on the first shell. It's closer to the nucleus in the first row. And this is true all the way up. It's harder and harder to remove the outermost electron because the outermost electron is closer and closer to the nucleus. Now what about the trend going left to right? Notice here ionization energy increases going left to right. It's the same argument we used before for size. As we go across any horizontal row, more and more protons are present in the nucleus, providing stronger and stronger attractive force on the outer electrons. And so it would be harder and harder to pull one of those electrons away, especially considering that as we go left to right, the elements are actually getting smaller, and those outer electrons are even getting closer to the nucleus, making it very difficult to remove them. So here again, our simple model, the Bohr model, allows us to predict with good success some trends within the periodic table. Now, something else you should be aware of, something that's observed many times, is that metals react by giving up electrons. So the metals on this diagram are those colored in beige, everything to the left of these purple metalloids. These are metals. Characteristically, metals readily give up electrons, whereas the non-metals, which are here the green colored elements on the right, they react by taking electrons. Now why would that be? Well, when a reaction occurs between metals and non-metals, the metals have the low ionization energy. It's relatively easy to remove electrons from a metal, and it's the non-metals that have the greatest attractive force on outer electrons, and they tend to want to pull electrons in to fill their valence shell, and they have the strongest force to do so. And that brings us to the next prediction we can make, and that is the charges of the ions that form from the representative elements. So as I just stated, the metals, which in this diagram are green, when they react with nonmetals, they give up electrons. whereas the nonmetals gain electrons. Now, considering that the noble gases are stable and unreactive, it turns out that the nonmetals, when they react with metals, will gain enough electrons to become isoelectronic with the nearest noble gas, meaning they will have the same number of electrons in the valence shell as the nearest noble gas. So isoelectronic means same electron configuration in the valence shell. Fluorine is only one electron short of having a full valence shell like neon, and that is how fluorine reacts. In all of its reactions, it is a nonmetal. It takes electrons. How many? Just one, not two, not three. Why not two or three? It only needs one to become isoelectronic with neon. The same is true for other group 7A elements. Chlorine, bromine, iodine. When they react with metals, they're going to take electrons from metals. How many? Just one to be isoelectronic with the nearest noble gas. Look at the group 6A nonmetals, just the nonmetals, oxygen, sulfur, and selenium. They will react with metals so as to gain 2 electrons, and that would make them isoelectronic with the nearest noble gas. They don't gain 3 or 1 or 4. They want 2, and they will do so when reacting with metals to become isoelectronic with the nearest noble gas, and so they will have a charge of -2. If we gain 2 negative charges and it was neutral, oxygen becomes -2. Sulfur, when it gains 2 electrons, becomes -2, and so does selenium. Look at the group 5A nonmetals. There's only 2 of them, nitrogen and phosphorus. They are 3 electrons short of having the valence electron arrangement of neon or argon, and so that's how they react when they react with metals. They gain 3 electrons to fill the valence shell, and they'll have charges of -3. We'll leave carbon out of the discussion for now. I'll simply say it's very difficult for any atom to have a charge of -4. It's just too reactive. It doesn't happen. Let's look at the metals. Group 1A metals, lithium, sodium, potassium, rubidium. Metals characteristically lose electrons. Why? We've just made the case that the ionization energy of metals is relatively low on the left-hand side of the table compared to the nonmetals on the right. So these outer electrons are far from the nucleus, they're loosely held, and they can be taken by the nonmetals. How many electrons will the group 1A metals lose? Well, they only lose as many as they have in their valence shell. They react to empty the valence shell. Now think about this with me. Lithium has 2 inner electrons and 1 outer one. If lithium loses the outer electron, it then is just like helium. It has the same electron configuration as helium. It's isoelectronic with helium, and that makes it stable. So lithium plus 1 cation is isoelectronic with helium. Now it's not the same as helium, because helium only has 2 protons, lithium still has 3, but lithium cation is far more stable than lithium metal. Look at the group 2A metals. Beryllium, magnesium, calcium, strontium, barium, and radium. They all have 2 valence electrons. When they react with nonmetals, they give away both of those 2 valence electrons. They empty out the valence shell. They don't lose 3, they don't lose 1, they always lose 2, forming +2 cations. Look at the group 3A metals, beginning with aluminum, gallium, indium, and thallium. When they typically react with metals, they will lose all 3 of their valence electrons, forming charges of +3 cations. And tin and lead below it, in group 4A, can lose 4 electrons to form a charge of +4. So here's a summary of what I've just said. Now I've put the noble gases in the middle of this table to make it easier to see. Here are the group 7A nonmetals. They need 1 more electron to become 2 and 8, 2, 8, and 8 like argon, 2, 8, 18, and 8 like krypton, 2, 8, 18, 18, and 8 like xenon. In every case they gain 1 electron and form an anion with a charge of -1. Here are the group 6A nonmetals, each of them gaining 2 electrons, forming ions of a charge of -2, anions. And here are group 5A nonmetals, nitrogen and phosphorus. They will gain 3 electrons and form anions with a charge of -3. And over here we have the group 1A metal cations, and these are the charges that will be formed when these metals lose their one and only valence electron. They all become cations with a +1 charge. Here are the cation charges of the group 2A metals. When they react with nonmetals, they'll lose both their outer electrons, forming ions with a +2 charge. Here's aluminum, gallium, indium, and thallium. When they lose all 3 electrons, they're going to have a charge of +3. And tin and lead, when they lose 4 electrons, they are metals, charge of +4. Okay, let's try one more time using our Bohr models and simplified Bohr models and Lewis symbols. Here we have a lithium atom. It's from group 1A. It has 3 protons and 3 electrons, 1 in the valence shell. If it could lose the 1 valence electron, that's what it wants to do, it becomes a +1 cation. So it had 3 protons and 3 electrons. It was a neutral atom. It still has 3 protons, but now only 2 electrons. Here's the one that's lost. The charge must be +1. Here it is in a Bohr diagram. This lithium atom loses 1 electron. There it goes. What's left is 2 electrons and 3 protons. Let's draw that with Lewis symbols. We'll say lithium is in group 1A. It has 1 valence electron. It goes to lithium cation, and here's the 1 electron that's lost. Now this arrow is like an equal sign. Whatever's on the left has to be equal to the right, and furthermore it gives us the direction. It says the left side is changing to the right side. So the total charge on the left side is 0. Lithium is neutral. The total charge on the right is +1 and -1, or 0. Furthermore, the mass is equal. So the mass of an electron is very small. I've taken it away, but here's that electron, here's its mass, here's the mass of a lithium cation. Together that mass is equal to the mass of a lithium atom. In group 2A, the elements have 2 valence electrons, like magnesium. Here's 1 and 2, and they characteristically react by losing those 2 electrons, and when they do that, they form an ion with a +2 charge. Because magnesium starts with 12 protons and 12 electrons, it's neutral, but if you take away 2 electrons, well, it still has 12 protons, but only 10 electrons, so the charge is +2. Here it is in a simplified Bohr diagram. Magnesium with 2 valence electrons will lose them. What's left? Well, that's only 10 electrons instead of 12. So we write magnesium in group 2A with 2 valence electrons reacts to produce a magnesium +2 cation and releases 2 electrons. And that's characteristic of other group 2A metals like beryllium, calcium, strontium, and barium. How about group 3A? We have aluminum, gallium, indium, and thallium. Let's take aluminum. Element number 13 has 13 protons, 13 electrons, but 3 are in the valence shell. They react by losing the 3 electrons, and so the charge of the cation must be +3. Here it is in a simplified Bohr diagram. Let's say the aluminum is going to lose its 3 valence electrons. Here they are. It's got 3 less, and this is a +3 cation. We would write aluminum with 3 valence electrons goes to aluminum +3 cation, releasing 3 electrons. The total charge is 0 on both sides. Let's look at some nonmetals. Here's fluorine. It has 9 protons and 9 electrons. There are 7 electrons in the valence shell. It would like to have 1 more. It's a nonmetal. Would like to have 1 more. Nonmetals want to fill up the valence shell. If it could take 1 more, it becomes isoelectronic with neon, and that's exactly what it does. Now if it was neutral, if the charge was 0, and it gains 1 negative charge, now it must be -1. Here it is in a simplified Bohr diagram. We add 1 electron to the 7, it now has 8. Let's draw that in the Lewis symbol. I would say fluorine with 7 valence electrons. We add 1 electron, and that'll form a fluoride anion with a charge of -1. Let's go to group 6A. Oxygen and sulfur and selenium are in group 6A. Oxygen has a charge of 0. 8 protons, 8 electrons. It only has 6 in the valence shell. It would like to have 2 more. And if we add 2 more electrons, then we fill it up, and now it'll have a charge of -2. Here's another way to look at it. We'll add 2 electrons to the 6 to get 8. It is now isoelectronic with neon. It'll have a charge of -2. So here is oxygen in group 6A with 6 valence electrons. It gains 2 more electrons. It's going to form an oxide anion with a charge of 2- or -2. Finally, we can look at nitrogen and phosphorus. They're in group 5A. Nitrogen has 7 protons and 7 electrons. It is neutral. 5 of those electrons are in the valence shell. It would like to have 3 more to fill it up to be like neon, and if it reacts with a metal it can do so, gaining 3, and now it'll have a charge, of course, of -3. Here it is in a Lewis symbol. 5 in the valence shell. Let's add 3. Now we have 8. Lewis symbol here. We have nitrogen in group 5A plus 3 electrons. It's neutral to begin with. We add 3 negative charges. It's going to have a charge of -3, correct? It's got 3 more negative charges than it used to have. So that's nitride, and phosphorus works the same way. So although our onion model or Bohr model of the atom is not completely accurate, it's very simplified, it still gives us a lot of good information. Round about the mid-1900s, physicists became aware that when atoms are energized, as through heat or electricity, they absorb that energy but hold on to it for only a very short period of time. I've read it's 10 to the minus 15 seconds. And they emit that energy as some form of electromagnetic radiation. And well, so let's talk briefly about what is electromagnetic radiation. The electromagnetic radiation is divided into 7 types, ranging from low energy, low frequency, long wavelength, like radio waves, and then moving in the direction left to right towards higher energy, higher frequency, and shorter wavelength. We have radio waves, then microwaves, infrared, visible, ultraviolet radiation, X-ray radiation, and gamma ray radiation. And the visible spectrum is what we can see with our eyes. That ranges from about 750 nanometers in the area of red light, moving towards about 400 nanometers red, orange, yellow, green, blue, indigo, and violet. So the atoms that are excited emit some type of electromagnetic radiation. Some of it's perhaps in the infrared or the ultraviolet where we can't see it, but some of it lands in the visible range where humans can see it. So electromagnetic radiation, when atoms are heated, atoms do not emit all types of electromagnetic radiation. In the illustration here you see a splint, a wooden splint that has calcium chloride salt on it in a flame, and it emits a very unique orange-red color for calcium chloride. And here we see a copper chloride salt placed on a wooden splint in a flame, and it emits a blue-green color. It's not red, it's not purple, it's not yellow, it's blue and green specifically. Each atom, each type of atom, emits its own specific unique wavelength or color. It's found that the energy that's being gained or emitted by atoms is not continuous, but it's quantized. So picture an electron trying to get up this energy incline. That's what happens when an atom absorbs radiation. The electrons move farther away from the nucleus. They stay there for an instant in time and then fall back. But they cannot go to any different position from the nucleus. They can't emit or absorb any wavelength of light. They can only do it in a quantized fashion, like climbing this energy staircase. The electron will absorb the energy, move away from the nucleus, landing on one of these stairs, and then immediately fall back. Each of these stairs represents a different energy gap within a shell. So this might be just, for example, perhaps this represents a yellow light absorption. Up here might be green. This might be blue and violet, and others that we can't see. We say that the energy absorption and emission by electrons, and therefore by atoms, is quantized, not continuous. So we can think of this as an energy staircase, but not a ramp. Here's an illustration that might make this clearer. So let's take a hydrogen atom with one proton and one electron in the first shell. Now, electrons will get as close as they can to the nucleus, owing to electrostatic attraction. And then this represents the ground state electron configuration, the most stable arrangement of electrons in an atom. Now, the atom can be heated. That would be a thermal excitation. And when that happens, an electron from the ground state will be promoted or jump into a higher energy level, perhaps into the next shell or higher shells. And that's an excited state. Now the electron remains there for a very short period of time, as you see here, and spontaneously undergoes relaxation. That electron falls back. When it does so, it gives off energy, goes back to the ground state. The energy of the photons given off are equal to the energy gap across which the electron dropped. So picture here one electron in the first shell. Now these symbols S and P I'll explain shortly. So for now, just let's say this is the first shell. In the ground state, an electron is in it. When thermally excited, that electron is promoted into an excited state into some higher energy level. Then the atom undergoes spontaneous relaxation where the electron drops back to the first shell, and in so doing emits a photon whose energy is equal to the difference in the energy gap across which the electron descended. And it turns out that every atom has different energy gaps in its energy staircase. And so every atom, every type of atom, will emit a unique spectrum of colors and wavelengths specific to that type of atom. It's like a fingerprint that we can use to identify which atom is being excited. It's a pretty powerful tool. It's called spectroscopy. So now we're going to refine or sophisticate our model of the atom a little further. It turns out that within these shells or layers around the nucleus, where the electrons are, there are subdivisions or subshells. We kind of alluded to this earlier, pointing out that in the second shell and beyond there were actually 4 subdivisions where electrons could reside. The subdivisions, the sublevels, the subshells, are called orbitals. Around about the 1920s, physicists Louis de Broglie and Erwin Schrödinger calculated 3-dimensional mathematical shapes of these orbitals, or energy shell subshells. And orbitals are simply regions of space, 3-dimensional shapes around the nucleus in which rapidly moving electrons spend 90% of their time. We had defined these before as just being layers, circular, hollow layers. Well, now we're going to say there's more than just that. And they're orbitals, and each orbital, regardless of its shape, can hold a maximum of 2 electrons. So in this picture, we're going to refine our layers a bit. Here we have the nucleus again at the center, and we have our layers or shells or energy levels. There are a maximum of 7. I only show 6 here. In the first shell or energy level, there's only one type of orbital. It can hold a maximum of 2 electrons. It is called an s orbital. It is spherical shaped. Here's an illustration of it. It's simply a circular, a hollow sphere in which 2 electrons maximum can be held. And it's called a 1s orbital because it's called an s orbital. S reminds me of spherical, and 1 because it's in the first shell. And that's all there's room for in the first shell. Remember, there's a maximum of 2 electrons per orbital, so 2 electrons only can fit in the first shell for hydrogen and helium. We get to lithium through neon. They can all fit in the second shell. Now in the second shell we said there's 4 divisions. Turns out there is an s orbital that's bigger than the 1s, so it's called a 2s. It's in the second shell, it's 2s. And there are 3 p orbitals. Let me show you those. So this would be the 2s orbital, which would be bigger than the 1s and superimposed on it. And here are the 3 types of p orbitals. There's a px orbital oriented on the x-axis in 3-dimensional space. There's a py axis oriented on a y-axis in space, and a pz orbital oriented on a z-axis in 3-dimensional space. Now they're called p orbitals. They look like dumbbells to me. One student said they look like a twin-bladed propeller, and a propeller has a P, and so does the name. Now you have to visualize these as being superimposed like this. Px, Py, Pz, all sitting on top of the 2s orbital, which is on top of the 1s orbital. So in the second shell, we have room for 4 orbitals. One is a 2s, and 3 of them are 2p. Why are they called 2? Because they're in the second shell. Why is it s? Because one of them is spherical, and 3 of them are twin-bladed propeller shaped. In the third shell, there are 3 kinds of orbitals. There's an s orbital called the 3s. There are 3 more p orbitals, the same shapes as before, but bigger and overtop those in the second shell, and they are called the 3p orbitals. And then there are 5 d orbitals. Let's take a look at these. The d orbitals look like, to me, double dumbbells. At least 4 out of 5 of them do. So there are actually 5 different d orbitals in the third shell and every shell above it. And remember, regardless of the shape or the name, they all can hold a maximum of 2 electrons. So actually 10 electrons in total could fill or fit into these 5 d orbitals. There's this third shell, contains an s orbital, 3 p orbitals, and 5 3d orbitals. In the fourth shell, which is larger and farther from the nucleus, there's a 4s orbital, a large circular orbital. There are 3 of these p orbitals called 4p because they're in the fourth shell, and there are 5 of these d orbitals called 4d because they're in the fourth shell, and now we have for the first time 7 of these f orbitals. Now an f orbital, let's take a look. These are f orbitals, and there are 7 of them in total. They look pretty much like triple dumbbells with the exception of 1. Notice there are 7 f orbitals, each one holding a maximum of 2 electrons, for a total of 14 electrons can fit into the 7 f orbitals that are present in the 4th shell and the 5th and 6th. We need really not go any higher because by the time we fill those, we have taken care of all 118 elements. So the model we've been using, this concentric layers of rings, onion layers around a center, is not great. It worked, but it has limitations. It turns out that some of these orbitals from one shell overlap into other shells. And a better image of these orbitals would look something like this. So here we have px, py, pz orbitals with d orbitals over top, on top of s orbitals, and you can perhaps appreciate here that some of these orbitals will fill in the wrong order. As much as we like them to follow the order we say, they don't exactly do that. And yet the filling order is important, again, for us to predict and understand how the atoms behave and how they react. So is there a way that we can learn the filling order without too much stress? And yes, there is, by looking at a periodic table. Alright, so here is our periodic table. Again, each of these horizontal rows are shells or energy levels, and there are 7 of them. The filling order is not a perfect sequence as we would like. The periodic table tells us what it is. Let me read several at the same time here. So here is the first shell is filled. In the 1s orbital, 2 electrons go in. And this is what this is saying here. 1s from hydrogen all the way to helium. Then in the second and third shells or rows, we have electrons filling the 2s orbital. Here's 2s, and then that's lithium and beryllium, and then we go over and fill the 2p orbitals. There's 3 of those orbitals, maximum of 6 electrons. That takes care of boron through neon. The third shell is filled the same as the second. The 3s orbital is filled, as we would predict, as we drew with our Bohr diagrams, followed by the 3p. So aluminum through argon, we're filling the 3p orbitals here. Let me go back up to this other view. So here we have 1s, then in the second period, 2s and 2p, same pattern in the third, 3s, 3p. When we get to the fourth and fifth periods here, this is where the first sets of d orbitals come into play. So this is 4s2, here's 4s, 2 electrons go in there, and then there are 10 elements in which electrons are filling the 3d orbitals. Remember, there's 5 of them, and there's room for 10 electrons. So take a look over here. It goes 4s, 3d, 4p. Here's 4s, 3d, 4p. And we can see this right on the periodic table. If you have a periodic table, it's easy to pick that out. Start here. 4 is 4s, 3d, and then 4p. 2 electrons go in the s orbital. 10 electrons can go in the 5d orbitals. 6 electrons fit in the 3p orbitals. Takes us to krypton. Now the fifth period is filled the same as the fourth. So we have the 5s, 2 electrons go in there. Then we have these 5d orbitals, the 5 4d orbitals. So they're 4d, and there's 10 electrons going to 5 of the 4d orbitals. And then we have the 3 5p orbitals taking care of the next 6 electrons right up to xenon. Note the pattern. 1s, then it's 2s, 2p, 3s, 3p, and here come the d's now. 4s, 3d, 4p, 5s, 4d, 5p. The fourth and fifth rows fill like each other. And finally, in the sixth and seventh period, down here, this is where the f orbitals come into play. So we have 6s orbital is one of them, takes care of 2 electrons. Then we fill the 4f orbitals. They're called 4f, and there are 7 of them. And 7 times 2 is 14, so 14 elements. From cerium all the way across to lutetium, there's 14 elements, and it's the 4f orbitals, 7 of them, that are being filled here. So it goes 6s, 4f, then 5d to Mercury, and then 6p. The seventh period, or shell, is filled just like the sixth. 7s, 5f, 6d, 7p. Take a look up here in the chart. 6s, 4f, 5d, 6p, followed by the seventh period, 7s, 5f, 6d, 7p. Note the pattern. Note the letters n, n-2, n-1, and n. So n is the shell number, shells 1 through 7. So here we have the fourth shell being filled, 4s, and then we have n-1d, that means 3d, and then np is 4p. In the fifth shell we have n is 5, n minus 1d would mean 4d, and np would be 5p. Then in the sixth and seventh shells, 6s, n minus 2 is 4f, n minus 1d is 5d, and np is 6p. In the seventh and final shell, n is 7, 7s, n minus 2 would be 5f, n minus 1 would be 6d, np is 7p, and that takes us all the way to Oganesson. If you can memorize the sequence of filling, and I think you can by looking at a periodic table, which you will have, you would simply say 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. If you can do that, you can write down the electron configuration of any element. And that's what we want to do. Let's get some practice doing that. I've written down the maximum number of electrons in each orbital. So each orbital holds 2. There's only one type of s orbital. So 1s2 means we have a full s orbital in the first shell. That would represent helium. Then moving across the second period, we have the 2s and the 3 2p orbitals. 6 electrons in the 2p orbitals and 2 in the s. That's a total of 8 more. 8 plus 2 makes 10. That brings us to neon. The third shell fills like the second. We have 3s2, 3p6. So that's another 8 electrons. 10 plus 8 makes 18. That brings us to argon. Now across the fourth period, or fourth shell, we have s, d, p. And we have then 10 more electrons can go into these 5d orbitals. 4s2, 3d10, 4p6. Well, there's a total of 8 plus 10 is 18. 18 plus 18 makes 36, brings us to krypton. The fifth is filled like the fourth. Again, we have s, d, and p. 5s2, 4d10, 5p6. That again, that's 18 more electrons. 36 plus 18 is 54, and that is xenon, the next noble gas. The sixth and the seventh each have a total of 32 electrons that can fit into them, because we have the s and the d and the p, which was 18, plus the f, which contains 14 more. 18 and 14 is 32. So from 54 plus 32 brings us to 86, which is radon. And the same is true across the seventh period. We have S, F, D, and P. Again, that's another 32. There's 2. Plus 6 is 8. Plus 10 is 18. Plus 14 is 32. 32 and 86 makes Oganesson, which is 118. In case it's not clear what I'm describing here, let me do a couple using Bohr diagrams. We are saying that we can write or describe the electron configuration rather than drawing these diagrams. We can do it with this alphanumeric notation. We would describe the electron configuration of hydrogen as being 1s1, meaning that there is one electron in an s orbital in the first shell. We would write the electron configuration of helium this way. We would say 1s2, meaning that there are 2 electrons in the first shell in an s orbital in the case of helium. How about lithium? Okay, so lithium has 2 electrons in the first shell and 1 in the second. We would write 1s2. Those are the 2 that are here and filled. Then we would say 2s1. So there's 1 electron in the second shell. In the case of beryllium, we would write the electron configuration this fashion. We would say it's 1s2, 2s2. You get the idea? So instead of drawing these diagrams, we can describe the distribution, arrangement of electrons And we'll need this when we want to look at the chemistry and how they behave. What would be electron configuration for boron? We'd say 1s2, 2s2, 2p1. 3 electrons in that second shell. Carbon, 1s2, 2s2, 2p2. It's in group 4a. It's got 4 electrons in the valence shell. Nitrogen, 1s2, 2s2, 2p3. So there's 5 electrons in the valence shell of nitrogen. You got the idea? Let's write the electron configuration for oxygen. You'd say 1s2, there's 6 in total in the valence shell, 2s2, 2p4. For fluorine, we would write 1s2, 2s2, 2p5. And for neon, we'd say the electron configuration is 1s2, 2s2, 2p6. Let's do sodium next. Sodium's electron configuration, there's a total of 11, right? So we could write this as 1s2, 2s2, 2p6, and 3s1. Now this gets rather tedious. These inner electrons are the same every time. What we could write is an abbreviated notation. We would say this part here, that's the same as neon. We could write it as simply this. We could say neon's 10 electrons, we'll put that in square braces, and then say 3s1. And it says the same thing but in shorter fashion. For magnesium, we could write its electron configuration as neon 3s2. What would you write for aluminum? Right? It's got 13 electrons. The first 10 are like neon, so we could say neon, and then the remaining 3 would be 3s2, 3p1. So these 3 electrons here in the third shell, that's what we're describing. First the S is filled, and then the P starts to fill. Silicon, we would write neon 3s2, 3p2, because there's 4 electrons in the valence shell. In the s orbital is filled and 2 in the p. In the case of phosphorus, we would write the first 10 electrons like neon, then we could say 3s2, 3p3. There are 5 electrons in the valence shell, and phosphorus is a group 5a element, so it's got to have 5. Sulfur, 6 valence electrons. 10 are like neon, and then we'd say 3s2, 3p4, like oxygen. Oxygen is 2s2, 2p4. Chlorine, 17 valence electrons. The first 10 are like neon, then we have 3s2, 3p5. What about argon? Well, the first 10 are like neon, and then we have 3s2, 3p6. And there are the 8 electrons in the valence shell, 2 in the s orbital, and the remaining 6 in the 3p orbitals. We got 2 more we can do here. Potassium. Now, rather than writing everything out, we could say the first 18 electrons are like argon, and here they are, the first 18, and then there's one more, so we'll write 4s1. Calcium would be like argon, first 18 electrons, 4s2. We can do that for any element. Let's take a look at bromine here. Bromine has 35 protons and 35 electrons. So let's count to 35. We'd say 1s2. then it's 2s2, 2p6. There's 8 more electrons. 3s2, 3p6, there's 8 more electrons. Where are we at here? Let's count. Okay, there's 2 plus 8 makes 10. So this is helium. Here's neon. 8 more makes 18, and that's argon. We get to the fourth period. It's 4s2, 3d10, 4p6. There's another 18 here. 18 and 18 makes 36, and that would be helium, neon, argon, krypton, but we only want 35, so let's take one away. Okay, we want 35, not 36, so that would be bromine, and that would be 4p5, not 4p6. So you can just track through this using the noble gases as a guide, and then add or subtract a few electrons as needed. How would you write the electron configuration of tellurium? It's got 52 electrons, 52 protons. The first 2 brings you to helium. At 8 more brings you to neon. 8 more brings you to 18, that's argon. We're right here now. And then we have the fourth shell, 4s2, 3d10, 4p6, that's 18 more. That'll give you 36. When you get to krypton, we want to go to 52. Let's try the fifth shell. 5s2, 4d10 would be 5p6 if you went all the way across to xenon. That would be another 18, which would bring you to 54. If you went to 5p6, which would be xenon, you'd have 54. But we only want 52 for tellurium, and that's why this says 5p4, not 5p6. That is 52 electrons. That would be tellurium. What if you were asked to write the electron configuration of iodine with 53 electrons? Let's count them out. 1s2 brings you to helium with 2. Right, that brings you to here. Then 2s2, 2p6 going across the second period, that brings you to neon. That's 8 more. So here we have 10 in total, and that is neon. Third period, 3s2, 3p6 brings you to argon. That's 8 more. That's 18, brings you to argon. Then we go to the fourth period. We have 4s2, 3d10, 4p6. That's 18 electrons across here. It's 18 more, brings you to 36, and that would be at krypton. We're getting close. That's 53. Let's go to the next noble gas. That'd be 5s2, 4d10, 5p6. 5s2, 4d10, 5p. If this was a 6, there would be another 18. That would be 54. We want 53, so let's take one away. Make that a 53, and that's why that's 5p5. That's 53, and that's iodine. What if you were asked to write the electron configuration of radium? Radium has 88 electrons. Let's count them out. 1s2, 2 electrons brings us to helium. 2s2, 2p6 brings us to neon. That's 8 more. That's element 10 is neon. The third is the same as the second. 3s2, 3p6 is 8 more, brings us to here, which is argon. 18, that's argon. Okay, the fourth period, 4s2, 3d10, 4p6, 18 electrons, brings us to krypton. 18 and 18 makes 36, that is krypton. We want to get to 88, let's keep going. Okay, the fifth is like the fourth. 5s2, 4d10, 5p6, that's 18 more, brings us to xenon. 36 and 18 makes 54. There's a xenon. Not there yet. We have to go to the sixth shell now. 6s2, 4f14, 5d10, 6p6 takes us to radon. Let's go ahead and add all those in. That's 6s2, 4f14, 5d10, 4p6. That's a total of 18 and 14 is 32 electrons. This is 86, and that would be radon. And we want 88, so we want 2 more. So there it is, 88. 7s2 brings us francium and radium. Radium right there at 88. Let's try one more. Let's say you had to write the electron configuration of livermorium with 116 electrons. We can count it out, right? The first shell, 1s2, 2 electrons, that's helium, takes us to here. The second shell, 8 electrons more, brings us to element number 10, which is neon. We've moved across here and now we're at neon. The third is like the second, 3s2, 3p6 brings us to argon. 3s2, 3p6 is 8 more, that's 18 electrons, that is like argon. The fourth shell, 4s2, 3d10, 4p6, here it is, 4s2, 3d10, 4p6 is 18, 36, that is krypton. We're getting there. The fifth is like the fourth, 5s2, 4d10, 5p6 brings us to xenon, that is 18 more, 18 and 36 is 54, and that would be xenon. Alright, now we're into the sixth shell, 6s2, 4f14, 5d10, 6p6. Here it is, 6s2, 4f14, 5d10, 6p6. That's 32 electrons. 32 and 54 makes 86, and that's radon. Here it is here. We have to go all the way to 116. Let's do the seventh shell. Okay, here's 7s2, 5f14, 6d10, 7p6. That would be, if we go all the way to 7p6, that'd be another 32, brings us to 118, which would be oganesson. But we are asked to stop at 116, livermorium. So let's just take 2 of those electrons away. That's livermorium. Right, so I hope that works for you, that you can write the electron configuration of any atom given the number of protons, and you have a periodic table that you can read these sequences, the filling order of the orbitals in. That's enough for this lesson. I hope that helps. Have a great day.